Ladies and gentlemen, I'm Hua Fan. The title is the Microsystem Design of Steering Angle Sensor. The content include 5 parts. At first, make a brief introduction. The applications of Hall sensor has many applications. For example, it can be used in consumer electronics, in automotive electronics, in electricity power transformation and automation control, and the Hall sensor has a very broad market. And it based on the basic Hall effect. Apply an applied magnetic field perpendicular to the direction of current to the energized semiconductor. The carriers in the semiconductor are subjected to the Lorentz force, and the trajectory shifted to S1 arrow tiled. With the accumulation of carriers and the potential difference between S1 and S2, carriers will be subjected to the electric field force opposite to the Lorentz force. And finally, the carriers are subjected to the Lorentz forces and the electronic field force to reach the equilibrium and forms a stable voltage V Hall. That's the Hall voltage. And the Hall devices is a rectangular, are typically designed in 4 contact configuration, with 2 relative contacts serving as buyers and the other 2 relative contacts serving as measurement ports for external magnetic fields perpendicular to the chip surface. This is the vertical Hall devices. Vertical Hall devices are typically designed in a 5 contact configuration where contact C is used to provide bias for the vertical Hall device, and the other 2 contacts are used as measurement contacts for external magnetic fields parallel to the chip. Now, we use the console to build the model for the Hall device. That's our flow difference. The FEA method refers the decomposition of the monolithic physical object or system into multiple discrete yet interconnected finite element modules. That's the FEM. FEM method is a popular method in COMSOL which has the advantage of defining the load conditions on structurally simple subnets without the need to consider the complex boundary conditions of the target system. First of all, we're building the geometric models, then we choose the materials which we need, and we must set the binding conditions in the COMSOL environment. After that, we have the grid division, and the grid division will discrete solver, and after that, we can do some data processing staging. That's the grid division in COMSOL. And this is our some simple model example. This is the whole device, and when apply a voltage and bias, we will get the whole voltage in the COMSOL. And this is our comparison of horizontal Hall for different structures. For example, there are a lot of shapes: rectangular, square, cross, and octagonal, and we can compare them in their current-dependent sensitivity and voltage-dependent sensitivity. For example, the rectangular has a much higher sensitivity than the square, and this is the effect of size on cross-Hall devices. In fact, we focus on our research on cross-Hall devices, and we have do some simulations. When we analyze the effect of the length of Hall device on the sensitivity, the current-related sensitivity gradually increases with the increase of length, and the sensitivity increases slowly with the increase of length when the length is greater than a certain degree, and the voltage-related sensitivity increases first and then decreases with the increase of length. So the length is choose to be 30 micrometer. Here, we can say that it's a cross point. And the fixed length is 30. After fixed, the effect of the width of the whole device on the sensitivity is scanned. In the right figure, we can see that the current-dependent sensitivity gradually decreases with the increases of the width, and the voltage-dependent sensitivity first increases and slowly decreases with the increase of the width. So we can see that there is also another cross point. So we choose the length and the width in according to our simulation. Analyze the effect of contact electronic length on the sensitivity of Hall devices. The current-dependent sensitivity gradually decreases with increase of contact electronic control length, while the voltage-dependent sensitivity increases rapidly from 6 to 12 and becomes flat between 14 and 20 with increasing contact electronic length. The contact electrode length of 10 micrometer can comprise the current-dependent sensitivity and voltage-dependent sensitivity. After that, analyze the effect of contact electrode length on the sensitivity of whole device. The current-dependent sensitivity gradually decreases with increasing contact electrode length, while the voltage-dependent sensitivity increases rapidly from 6 to 12 and becomes flat from 14 to 20 with increasing of electrode length. The contact electrode length of 10 can be compromised the current-dependent sensitivity and the voltage-dependent sensitivity. So we also choose a cross point, which has a good simulation result. And the cross-Hall device simulation result can be concluded here. This is the parameters which we choose according to the COMSOL simulation. First of all, we based on the 180 nanometers, and the size of the cross-horizontal Hall device is 30 multiply 18. The contact electrode size is 10 multiply 2, and the thickness is 0.34. Current dependent sensitivity, after that we get 165. It's comparable high, and the voltage dependent sensitivity is 0.05, and the resistance at zero magnetic field is about 3 kilo. So the surface of the active region of the N-well is covered with a thin P+ injection layer to reduce the noise of the whole device. But in the actual experiment, we have made some trips with the P+ and without P+. The measurement results show no obvious difference. So sometimes the experimental and the simulation has a little gap. That's comparison of different structures of vertical Hall device. We have found that the 5 contacts, 4 contacts, and 4-folded 3 contacts, among them, the 4 contacts has a higher current dependent sensitivity and a higher voltage dependent sensitivity. And this is a comparison of different structures of vertical Hall device. And this is 4 contacts, 5 contacts, and 4-folded 3 contacts. We can see that when without the magnetic field, the offset is almost higher of the 5 contacts is 124, and after that, the 4-folded 3 contacts have the smallest offset. So comparison of the vertical Hall for different structures, we can get a conclusion. The advantages of four-folded three contacts has good effect of spalling current to eliminate misalignment and small initial mismatch, and we just find that it has the smallest offset. But its disadvantages, it has complex structure. And this is the effect of size on four-folded three-contact Hall device. We can say that align the influence of the length of the Hall device on the sensitivity. The current-related sensitivity increase gradually with increase of the length, and the sensitivity increases slowly with increase of length. When the length is larger than 30 and the voltage-related sensitivity decreases gradually with the increase of the length. So the length at finally is set to the 28 after discounting the current-dependent sensitivity. And the length was determined to be 28 and the effect of the width of Hall device on the sensitivity was analyzed. The current-dependent sensitivity decreased gradually with increase of the width, and the voltage-dependent sensitivity increased first and then decreased slowly with increase of the width. So finally, the width is setting to this point 1.4. So this red circle demonstrates the best simulation result, and in the practical design, we choose the red circle, and this is effect of contact electrode spacing. When we analyze the effect of contact electrode spacing on the sensitivity of Hall device, the current-dependent sensitivity gradually increases with increase of contact electrode spacing, and the voltage-dependent sensitivity gradually decreases with increase of contact electrode spacing, and the current-dependent sensitivity and the voltage-dependent sensitivity are moderate when the spacing is 6. So we choose this red circle point, 6 micrometer. So this is a four-folded three-contact vertical Hall device. When we design it, this is our parameters. For example, the size is 28 multiplied 1.4. The electrode size is 2 by 2. The thickness is 0.6. Current dependent sensitivity is 100. Voltage dependent sensitivity is 0.0, and the resistance is about 6 kilo. And finally, we will introduce the modulation of the three-axis Hall sensor. The main function is to measure the angle. This is the conventional three-axis Hall sensor implementation. At first, the three horizontal can constitute a three-axis Hall sensor, and in the middle, 4 horizontal and plus 2 vertical can also constitute three-axis sensor, and finally, horizontal plus magnetic concentrator can also make the three-axis Hall sensor. But this magnetic concentrator is a special process. For example, the Belgium the company the Belgium use the special process to fabricate the magnetic concentrator. And the three-axis Hall sensor implementation solution. This is our solution. We use the standard CMOS, and this is our simulation result. And we have 65 microvolt mismatch after complete of the two devices, which means that we use two devices complementary. And the three Hall sensor implementation solution. This is our 1, 2, 3, 4, 4 in the plate, and we use them to complement the offset of each others. And this is our simulation result. Finally, we only get 8 microvolt mismatch after the coupling of the 4 devices. That's our final resolution. And this is the folded axis to measure the y and z. And this is our simulation result. We can say that finally only 52 mismatch has remained of the two vertical devices. And finally, this is our solution. We use the four horizontal and the four, 1, 2, 3, 4 to constitute the vertical devices. This is our simulation of angle because the most function of the three-axis Hall sensor instrument is angle. So we can do the simulation in the console. And we found that the ideal and the measurement is the error is only 0.05. And after that, on the next theta, we can also calculate the angle error. It's about 0.25. So device and the model has finished, and we must do some interface circuit. This is a spiraling. This is the resistor model inside of the Hall sensor. This is our interface circuit. After the whole device, we have spinning circuit and amplifier, the correlated double and sampling, subtraction, and sample hold low pass filter. So this is our finally simulation result in the cadence. We can say that if we apply a magnetic field across the chip, and we can also get the Hall voltage also assigned. And this is our concluding about the effect of magnetic field intensity on Hall voltage. At last, we can say that sensitivity temperature drift is about percent 0.045. This is our interface circuit layout. This is concluding of parameters of all of the Hall sensors. So this is our summary. Thank you very much.
Thank you.
Thank you.
From which material is this whole sensor built? It's from semiconductor.
Yes, it's a
And
semicon.
what is the location?
SMIC is in China. The factory called
Yeah.
SMIC. It's a China technology.
Okay, thank you very much.
Thank you.
So